last lecture, as I will show, you rise to a paramagnetic contribution, which is Pauli spin paramagnetic. Okay? Whereas later on, that means tomorrow's talk, I will cover what's called the Landau paramagnetism, which is the diamagnetism that arises because of the orbital motion of the conduction element. Okay? So these are specific to magnets. That is, Pauli spin paramagnetism and Landau diamagnetism are specific to metals which have real conduction. Okay? So that is the background for this lecture. Now, before I start with this lecture, let me caution you that the subject I am going to cover today is rather difficult in the sense that there are EK diagram. Okay. Now instead of EK, I will talk in terms of the density of states. EK diagram you are familiar with, because that is for a free electron, a free particle, which is p square with or h cross square, k square. So here, the density of states for a free electron gas, you remember what is the density of states? Goes as, what does it depend on energy? So root E. Right. So it is for. So this, when I plot it like this, energy goes to this, then it will be a parabola. I call it spin up, spin down. Now field. Okay, this is true when there is no applied field. Okay, and the number of spins in the spin up subband and number of spins in the spin down subband are exactly equal. So that magnetization, which you define as this is the magnetization of the system, where n up is actually the number density of up spins, and down is the number density of down spins. Okay? And so this is nothing but the population difference between the two subbands, spin up and spin down subband. Difference in population is the magnetization. But for an electron gas, in the absence of any external field, then all the spins, all the A states are occupied by spin up and spin down. Okay? Two electrons with spins and parallel. So you have a spin up subband, a spin down subband, number of spins in the spin up and spin down subbands are equal. That is the same. Right? So that the population difference between spin up and spin down subbands is zero. That means there is no magnetization, no net magnetization in the absence of an external magnetic field for an electron gas. Is clear? Now, if I apply the field, suppose I apply the field of this direction, then how will this get one? Now you know that the energy, for example, yesterday, okay, so if you are dealing with this, U is nothing but one Bohr magneton for an electron. So it's just minus mu beta h. Okay? Or if you want, you can just, if I'm dealing with only spins, as I said that the diagram will ignore completely the orbital motion of electrons, we'll concentrate only on the spins of the electrons. And so then the G factor is 2, because these are spin only value of G. And so what will happen is, now if I have this, because this is G mu beta S, let me write it. There is no confusion. Okay, and so this is S. If S is half, spin half electron, so then this is less ms, right? And for electron, ms can have values, right? So for a spin up, for which ms is plus half, this would be just simply mu beta h minus mu beta. Okay. One thing you should remember is that this, whether the spin up energy will go up, whether the spin up energy goes up or down is decided by the sign of mu b. Right? So mu b, we know what is mu b. Right? Now if I absorb the sign of E into E itself, it should be negative. If you just absorb it into E, then it may look like a positive quantity. Otherwise, sometimes some books will find that they define it like this. Okay, so we take a split sign. Then what will happen is, whatever I told you, will be just opposite. It means the spin of electrons will have higher energy, minus sign, and the spin down will have lower energy. So I am using this so that there is no confusion. So that means I now put this mu b treated as a positive. Then for spin up, the energy will be lowered by G mu beta of H. So G is 2. So it's just energy is lowered by minus mu beta H. Similarly, for spin down electrons, energy is increased by mu beta H. So this diagram will change. Exaggerating it will not be so much, but just for making it obvious. Clumsy, a bit word problem. Okay, so this is T not equal. Okay, so for the time being, I am not getting into T not equal to 0. That means that we are talking about 0 temperature, exactly at 0 temperature. This can be modified later on, because if at T not equal to 0, what will happen is there will be a thermal smearing of the Fermi energy. Okay, there will be a thermal smearing of the Fermi energy. That means then there will be derivatives of the Fermi energy, at Fermi energy, energy derivatives of GE. You have to compute add here, and then you have to take into account thermal smearing of the Fermi surface, which is very, very small. Okay. Compared to, because that is just within K beta T of, this is, let's say this is K beta T. K beta T is a very small, even at room temperature. You remember what is K beta T? atom temperature? 25.6 million volts. And what is the order of EF? EF would be tens of electrons, roughly. The order of 10 electrons, roughly. Okay? So obviously that cavitation is very, very small compared. That means the number of electrons that are actually getting excited, that is very, very small. Okay? So thermal sparing of the boundary surface is going to be very, very small unless you go to the Fermi temperature. Okay? There, of course, there will be then it goes into temperature. Okay? So now at t equal to 0, if I have energy, infinite energy, there Fe is 0, right? And E is infinite, is well above EF, there Fe is 0. So this, because of Fe infinity 0, so it is 0. So this term is 0 at this. When E is 0, GE, this G is 0, is 0. Right? Here. When E is 0, the answer state is 0. Right? So the first term here would contribute 0. So we are left with only the second term, which is this. Now, if you are dealing with only at absolute 0, then this DFE this effect for what do I get? This is versus energy. Okay, so how will that curve be? At absolute 0, which is this curve. If I take the derivative of this, then what will you get? So this, now here, this is going to be like a delta function. Derivative will be 0 on either side of here. At absolute 0, so this is a step function. So you have just this, right? So since I have this minus sign there, so I can write it as a delta function, delta E minus here. And so then the Pauli spins us to the limit. Is just doing this. Okay? So it is proportional to the density of state at Pauli. Okay. Now this was Pauli spin magnetism. If you have to calculate Pauli spin susceptibility at finite temperature, then smearing of the photo surface will come. And now instead of this, what will happen is that you will have right? This is thermal smearing. So now you can't treat it like this, but then this derivative is finite only within k beta t, k beta on either side, 2 k beta. Only within that, this has some reason. Otherwise, this is 0. So I can again make some approximations and change the limits from minus infinity to plus infinity. Okay, and only this energy interval that integral will contribute. Otherwise, all other places or for all other energies away from Fermi level, they will not contribute, they will be 0. Right? Okay. Now, this is one very important thing which, as I was telling you, things are not that easy, especially when you are dealing with itinerant magnetism. Okay? Because, as I said, there are very few textbooks on this itinerant magnetism. because it's not a simple concept. Most of the people have used what is called the localized spin picture, or Heisenberg model, okay, who gave actually the exchange interactions. He gave the concept of exchange. And because of that, then we could understand what is that molecular field, where does it come from, why the exchange has to be positive, the exchange integral has to be positive for paramagnetic, or it has to be negative. Okay? So those things came later. The child will in a later lecture will give you about how do you get the exchange interaction, which is called the direct Heisenberg exchange, which was the basis for this molecular field that was proposed by Weiss. Okay? You remember Weiss? Okay. Experimental observation, as you know, for iron, for example, if you take iron has a ground state moment of 2.2 volt. Okay? Iron has 2.2. Cobalt has 1.7. Nickel 0.6 moment. Now, if the localized picture would have been done for iron, cobalt, nickel, then you would have expected an integer value. No, it is not integer. Right? Am I making sense? Okay? So, outside Coulomb repulsion. Okay, and some of you who are doing some spin density calculations, they call it Hubbard unit. Right? So, this is the on-site Coulomb repulsion that these electrons experience because of the charge. So, then this potential energy is nothing but 1/2. I have now substituted for this. So, you get U times GEF du whole square. So, now what I have to do is the total energy should be the kinetic energy and the potential energy. So that is this. So now I have the form like this. Okay. Obviously, if this delta E, which is the sum of these two, if it is negative less than 0, then that would mean that this should be greater than 1. Okay? This should be greater than 1 for this change to be negative. So in that case only paramagnetism can survive. Okay? That means if the potential energy is much more than this, then you have this term. That means when U times GEF is greater than 1, then only there is a possibility of paramagnetism. This is called Stoner criterion for paramagnetism. What Stoner criterion for paramagnetism? One thing I would like to tell you this, which is not written here, is that when I am talking of paramagnetism, paramagnetism does not arise from S space. It arises from D space in iron. Right? Because it's primarily because of the D electrons, which are not partially filled issues. Where you have a net spin. Okay? And why it is so? Why only D electrons will contribute? Why not S?
Orbital size of the orbital is large and they can interact each other. The exchange.
Remember that the electron wave functions for let's say 4s. Okay? 4s electrons, the electron wave functions are more extended compared to the 3D. Right? So there is a more overlap of the electronic wave functions for S electrons than for D electrons. Is that clear? So that bandwidth for D dA electrons is smaller than that with S. So when the bandwidth is large for S electrons and D electrons have very narrow bands, that would mean the density of states at the Fermi level is mostly contributed by D electrons. D electron density of states are much higher order of magnitude, higher than S density of states. Okay? So it's largely governed by the D density of states. Although S will also contribute, but that contribution will be very small compared to the D contribution. Okay, this is one important thing which is not here, I have not written here, but this is what is implied. So now, if the Stoner criterion is satisfied, then there is this splitting of, there is an exchange splitting of the spin up and spin down bands, and that splitting is just this L. Okay. This is the absence of X only. Okay. Now, in those cases, 1 minute. So I said that if this is large compared to 1, then only there is momentum in the system. Okay? So that would require that both U as well as the density of state at the Fermi level should be large. Otherwise, that condition will not be satisfied. So the requirement is both U as well as G, EF should be large enough compared to 1. But it can happen that condition is not satisfied. You may have reasonably large values for U and G, EF, but yet the product is not, is close to 1, but not greater than 1. In that case, what happens? Then you can see yourself. Now, what we do is, we try to calculate the susceptibility in that case. In the case where the product of U and G, EF is close to unity but not greater than unity. Okay? In which case, then the energy, just remember, we have now included, because to get the susceptibility, you have to apply the magnetic field. Okay? You get the magnetic response from the system, you apply an external magnetic field and see how much magnetization finally develops corresponding to that field. That will decide the magnetic response from the system. Okay? So you now add this U1 term minus m dot. Okay? Otherwise, the remaining thing is the same. So now, here I have substituted this in terms of, because this can be written in terms of m is nothing but this. So I have just written this now here in terms of m. This is m square. Okay? So this is m square divided by this into this. So the equilibrium state of the system is when the derivative of that whole function with respect to m is 0. Okay? So that gives you this, so that the magnetic susceptibility can be reduced. Okay? So now what do you see? You see that when you do not take into account the Coulomb interactions, so U is 0. We have not taken into account any Coulomb interaction, then the susceptibility that we measure is just practically Pauli susceptibility. Okay? But with the Coulomb interactions and also the molecular field, okay, what has happened is now it has brought in this factor. This factor, when this product comes closer to 1, this starts going up. High value will shoot up. Understand? This is called the Stoner enhancement factor. This factor, 1 divided by this, is called the Stoner enhancement factor, because it enhances the Pauli spin. Now, if this spin up pole and spin down electron move individually, they see individually the mean field. Mean field is proportional to this, right? Splitting is coming because of the molecular field or exchange, right? This is not a picture in the magnetic field, remember. This is in the absence of any external field. This is the spontaneous splitting of these bands, subbands. Okay, in the absence of any external field. So now what happens is that if these spin up pole and spin down electron, if they don't form a pair, and they see this exchange field independent of each other, and both will react to that field. Understand? Both will react to that field different, and they are independent of each other. So that's why it's called Stoner's single particle excitation. This amounts to an excitation because this is a higher energy than the ground state. Ground state would have been when this was just occupied core. There is no hole that because we have not moved any electron. All those things are filled up to the permeate. Okay? So this is what is called the Stoner's single particle. We have some things that you not see. Anyway, here what is happening is that this case is not weak eternal case. Okay? So in weak eternal case, you had both the subbands fill up to this level, which is in there. Okay? And now again same thing. You take the spin up electron and put it in the spin down. Okay. So you have a spin up pole and a spin down electron. But now in this case, they make a bound pair. Okay? They make a bound pair. Like in the semiconductors, you have excitons. Right? You have electron hole pairs. Holes in the valence band and electrons in the conduction band, and they form pairs. It's a bound pair. Similar type. So you have this electron hole pair. And this electron hole pair hops from one side to another side. In the Q space, hops from one side to another side in the Q space, which is the reciprocal lattice. Okay? Reciprocal lattice space. In the direct space, they are localized. In the direct space, they are localized. In the K space, they are delocalized. Remember? That is how these two spaces are related to each other. In the direct space they are localized, then in the indirect space they will be delocalized, and vice versa. So this excitation is this spin wave excitation, where electron hole pairs hop from one atom to another atom in the K space. These are also called propagating transverse spin fluctuations. Also called propagating transverse spin fluctuations in the Q space. Whereas in the direct space they are local. So in eternal case now we have two types of excitation. One is the Stoner single particle excitation and the spin wave excitation. Now this is an important thing which I just skipped. Here what happens is that what is the probability that the electron will jump from one side to another side? Okay? That probability is given by, or that time it takes to jump from one side to another side, d is given by that time. Order of h by W is the bandwidth, right? The bandwidth is a Heisenberg uncertainty. Nothing but the Heisenberg uncertainty, where tells you that the time of hopping for d electron is h, Planck's constant, divided by the density, the width. Bandwidth. And if you take the typical bandwidth of order of 2 electron volts. Okay, so you will see that this time now we are doing the order of minus 15 seconds. Okay, now that means that even in the ground state at absolute zero, okay, there are very strong quantum fluctuations that take place because of this hopping of electrons, the electrons, let's say, from one side to another. They hop at this distance. So there are very fast quantum fluctuations. Now, if you are measuring this phenomenon, you are looking at the system, the time window, was your time window is of the order of 10 power, let's say, some which is higher than this, something like minus 6 seconds or minus 10 seconds. What will happen is that these quantum fluctuations will get averaged. Right? That is fluctuating. So when you take the time average, there will be some average value, and so the magnetic moment that you will see will invariably be non-integer. It will not be integer. Understand? Because it is going back and forth, and then suddenly you just time average. So it will have non-integer values. That's the reason why for itinerant magnets like iron or nickel, you have non-integer values of magnetic moment in the ground state. Okay? So this is one important thing. Okay. Another important thing is that one is this time scale. Another time scale which is associated with the excitation of spin waves. Spin wave excitations have a time scale of, or energy scale. What is the energy scale for the spin waves? Not micro. Milli-electron, because your spin wave stiffness, typical value would be of the order of milli-electron volt angstrom square. Right? So it will be of the order of milli-electron. Doesn't mean that it's discrete. Because if you do that, then for k equal to 0, you have so many energies. Right? That doesn't make any sense, because actual mode is this, that in this form is actually equal to 0. Right? This is the long wavelength mode, which requires the least energy to get excited. So as you go to higher, larger wavelengths, with smaller wavelengths, then you find that you have to give more energy to excite those, but then there is a continuum. Continuum in the sense that it is you have to traverse this curve, not like this. It means for a given value of k, this is the value of energy. For another value of k, this is the value of energy. So on. Okay? So that is a misunderstanding that created by many of these textbooks. You think that there are so many values, and these are scaled up to this is EF and so on. Which is completely.
Sir, for Pauli paramagnetism, that expression where magnetism equals to mu b square multiplied by field multiplied by density of states at Fermi level. So can one use this M versus H isotherms to measure the density of states in that metallic system?
Yes, for those cases where you can measure Pauli you can calculate. In fact, that is one of the methods of getting density. But then it is possible only in certain cases. You cannot get it in every case. First thing, it has to be a metal. Second thing is that it should be away from the chromatic instability. Right? So the metal should be such that there is no possibility of chromatic orders. Okay? So you have to choose a proper case where you can measure. There is an enhancement for the I said PT and PD case. This is enhancement of the density of states. Then that creates the enhancement in the density. So that enhancement is happening because the density of states are getting increased. So increase value of density of states. Or a given value of U. So then you can directly measure, or you can also get it for specific. If you measure electronic specific.